Hi, this is Mr. Yeager, basically going into video number 2 on rotation, where I'm looking at now basically this question is what causes an object to rotate? We're going to look at this scenario primarily through static equilibrium, so I say what is causing something to rotate, but we're not going to allow any rotation during this PowerPoint, but we're going to talk about what will cause basically a rotation. We're going to define this idea of torque and then look at it in a static equilibrium situation where there is actually no rotation, where basically the torques on opposite sides are balancing each other. In the next video, we will look at what happens when those torques don't balance each other and the object does actually begin to rotate. Okay, so here we go. So what causes an object to rotate? All right. So usually with this, people will go, well, a force. Okay, a force. That is partially correct. You do need to apply a force to obviously make anything begin to move, but the idea here is I can apply a force and make it move but not rotate. All right? So I need to look at what direction am I going to apply this force in relation to what? Okay? And so that's what we're looking at now is a force alone won't make an object rotate. Okay? It's needed to make it rotate, but so is another part, okay, in terms of how it gets applied. All right? And so, like the example, obviously, we use in the classroom all the time. I mean, I do, standing at the door, and it's just a standard one. What direction do I push the door to make it rotate on its hinges? Okay, and that would be where basically I create a force that's perpendicular. This is like more the official definition. I apply a force that is perpendicular to the distance from the fulcrum. Okay, in other words, that door is facing me, I come straight at it perpendicular, and I can apply a force to open up that door, as long as I apply it away from this thing called a fulcrum, which we'll obviously define in a moment. Okay? So there are some parameters with it. It's not simply a force. Okay? And so what we have here, okay, obviously, is like I'm saying, what did I just say there? Okay, I apply a force perpendicular to a fulcrum. All right. So here's my example of basically pushing a door. Okay, we have the fulcrum is down at the end here. That's where the hinges are. I'm going to apply this force exactly perpendicular to the door. This would be obviously a 90-degree angle. Okay, perpendicular to the door, and I push it a distance, which this is very old terminology called a lever arm, but this would be our distance from that fulcrum. So let's get all these definitions out here. Okay, the fulcrum itself is that rotating point. All right, there must be some area on it that I am pushing that the object's going to rotate around that particular point, and that is the fulcrum. Obviously, hinges on a door, axles. I mean, you can see all the examples here. Okay. A lot of times we think of like a seesaw. It would be obviously the piece in the middle that makes that the seesaw rotates up and down, back and forth around. Okay. The lever arm, which really is not used too much, again, it's more old terminology. I would say in AP Physics 1, we primarily just say the distance from the fulcrum. But if you happen to see the term lever arm, that is the distance between where you're applying the force and the fulcrum. In our formulas, you're going to see this as D perpendicular, okay, or R perpendicular, depending on how they try to illustrate it. So I like to use D perpendicular, but on your formula sheet, it's written as R perpendicular, the radius from that fulcrum. Because again, technically, if I rotate this all the way around, I'm going to make a circle all the way around. That is the idea. So that's why I still say radius. Okay. So that leads us to officially this term torque. Okay? And the symbol for torque, it looks like a T. It's actually the letter tau, the Greek letter tau. All right? On the formula sheet, it more often looks like this with the little curve at the end of it, basically like a backwards J. But that is the Greek letter tau. All right? So torque is officially that definition I gave 2 slides ago. It is the product of the force multiplied by this lever arm, the perpendicular distance from the fulcrum. Okay? And there's your standard formula, FD perpendicular. I mean, on your formula sheet, it can be written as tau equals force perpendicular D or force perpendicular R. All the same stuff. We have to obviously get used to the fact that, you know, I just think it makes more sense to call it D. And you'll see some textbooks that say it that way as well. But R, I guess, is our standard on our formula sheet. Okay? So it's just the formula between force times distance perpendicular. Okay? So we only want to look at that perpendicular force, that perpendicular distance from the lever arm. Okay? Is what we're looking at there. All right? Which that's going to come in play some. The units for force, we just combine the two units. It's Newton meters. Okay? Newton meters. Let me take a quick step back here. Some people might get confused by this early on because they're going, wait a minute, we have another formula that's force times distance. All right? We said work back in the energy unit is force times distance, but this would be the parallel force. So that's the thing is that these things are not the same. Work and torque are not the same as each other. Okay? And so therefore we're looking at it in terms of it is creating this rotational motion rather than obviously providing energy to the object itself. Obviously torque we'll get to that. Torque will will help create some rotational energy, but we'll talk about that a little bit later as well. Okay? All right. So kind of your initial problem, if a door requires 200 Newton meters of torque to open, explain why it would require more force closer to the fulcrum than away at the doorknob. So this is again why they put the doorknob so far away from the fulcrum. Okay, I mean pretty obvious example here. Here's your doorknob, here's the fulcrum. Okay, what we're looking at is this door. Every object has a particular amount of torque required to rotate it. Okay, so that's almost like the standard. There's a torque necessary to begin the rotation of that object, to overcome its rotational inertia and make it begin to rotate. All right? You can adjust how much force you apply to that object depending on the distance that it goes. So this is why the doorknobs are at the end, because if we have if we increase the distance, I can decrease the force that I need to apply perpendicular. Obviously, if you've ever tried to push a door, and again, in the classroom, like I obviously illustrate this, I mean, everybody can kind of understand this. If I start pushing the door really close, now my distance is very small, so I'm going to have to apply a larger force perpendicular. Okay? So that's why it's easier to rotate things at the end at far distance away from the fulcrum than very, very close. And this is obviously why we have different machines as well to allow us to do this maybe from a farther distance so we have less force applied. I mean, even just think of a hammer. You get more force. I mean, you don't have to apply as much force and still get just as much impact, essentially, on that nail from the very end of the hammer. While if you hold it really close, you kind of have to really smack, apply a lot of force to twist, to rotate that hammer to get that nail in. So that's why it's easier with a larger hammer, or obviously with a sledgehammer, even larger distance, okay, trying to go that around, especially if it's heavy, okay? So they are inversely related. The force and the distance are inversely related to each other. All right. So what happens if I push at an angle? All right. Because I mean, a lot of times you're not going to go straight at a door and go, "Let me make sure I'm perfectly perpendicular at this," and then start pushing. All right. You might be flying by and that door might be kind of closing on you, and you just kind of swat it away. All right. Does your entire force actually rotate the object? The answer to that is no. Okay. We are not going to have this entire force involved. We are only going to be including the perpendicular component. Okay. And so that means we actually have another version of torque, which we call it FD sine theta. So again, you can see a lot of similarities already between like the torque and work formulas. The thing is, they are not analogs, like I said in the last unit. Okay, torque is not an analog for work. They are not the same at all. Torque is close to force, is pretty close. Is semi-analogous to force, but again is not the same exactly as force. All right. So I mean that's where some people try to start making those analogs like we did with the kinematic values. So right here we would have to basically identify this force perpendicular using the angle, and that angle will always be given in a way that you have to use the sine theta function. I will say I have seen some problems solved without using the sine function, actually people using the cosine. So that's where I'll admit it's always made me wonder, like, why does it have to be FD sine theta? And it's based on basically the perception of how you're approaching the problem that it should be FD sine theta. And then just like how it was always cosine theta for work, the way we perceived that problem. So just be aware of that if you feel like you happen to feel like it could be switched. But this would be the formula that we'd always go to. It's given to you, again, on your formula sheet. Okay? So this would only be a partial force. We would still say this force causes, yes, it does cause it to rotate, but only the perpendicular part makes it rotate. We wouldn't use a whole force in the problem. Okay? So if I have this quick example here, okay, rank these from greatest to least in terms of the force acting on the door. Okay, if I did a little ranking task with it, all right. Again, we probably would like some numbers with it in some way. All right, we would like to know probably the angle. Okay, we would love to know what the angles are that these are pushing on the door. What is that angle? What is this angle? So we could do the FD sine theta to figure out the torque. But again, the idea here is all of these have to apply the exact same torque. Okay, so torque is a constant on all of these. What we're looking at is obviously distance is not and force is not. Okay, the forces and distances are being applied or not. Just from a general look at this, if I just had to take a look without them giving any numbers or anything, we would have to say that the greatest force would be C, and that's because it's so close. Okay, it has the smallest distance, so it has to have the greatest force. In addition, that it's at an angle. So that angled forces are only going to be larger than their perpendicular counterparts because, again, only the perpendicular components making it move and has to be a high enough number. Okay? So C would absolutely be the greatest. I'd have a real hard time trying to say that C is not the greatest almost with any angle based on the distance that it is from the fulcrum. Okay? The other two I've had students argue about a little bit because they're like, well, B looks like it's right in the middle and A is at the end, but it's angled. But the thing is, and they go, well, what's the angle? I can understand that if the angle was very, very, very extreme, that maybe A would be greater than B. But I'm looking at this primarily as a distance ranking, so I would say C is greater than B is greater than A. Now again, there is a possibility that A could be greater than B if it's at such an extreme angle. That's such an extreme angle. But if we don't want to overthink it. If it's given to you this way, I would definitely just go with CBA based on the distances. If they give us the angles, then I go back and calculate some. Let's just make it clear. Why would a force applied exactly as I drew there not make it rotate? Because this force is parallel with the distance to the fulcrum. So a parallel force, that would just be you pushing right into the fulcrum, and that object should not rotate at all. It will not rotate if you push it exactly parallel. Obviously, if you have an angle, it's going to shake the door a little bit, okay? But if you push straight at the end of the door, straight toward the hinge, it shouldn't rotate. Okay? So, is a torque required for an object to rotate? Yes, 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 yes. That's basically that one. All right. So this now leads us to what we're going to bring in called net torque. Okay. We're going to see this as torque net. Okay. Net torque. Right. Sorry, just looking at something. So net torque. But we're looking at this in terms of balancing. All right. Balancing. So that means the object is not rotating. It is perfectly balanced. It is not in rotational motion at all. So that would mean, okay, we're looking at basically problems where it's a suspension bridge. Why doesn't it flip? These would be like your rope bridges where it's like they're tied on both sides. Why isn't it, when I step on one side, why doesn't it rotate back to the other side? There must be a counter torque to it. All right. And again, this is even true even if there's more people on one side of the bridge. Why doesn't it basically break and start rotating around like an Indiana Jones, like flying across the bridge scene where he cuts the rope? All right. Are there perpendicular forces that could make the bridge begin to rotate? We will see yes. Okay? If I'm on a bridge that's basically suspended by two ropes, and I'm standing on that bridge, I am applying a weight straight down. Why can't this bridge rotate basically counterclockwise? Because I am applying a perpendicular force. All right? So there are perpendicular forces acting on it. All right? There are torques acting on it. All right? Come on. And again, this is the example I'm saying is, these movies where they cut the line and the person swings across. That could be anywhere. I mean, that could be something where they're tied at the top of a building, they cut the line, and then obviously swing all the way around. Okay? So that would obviously be a torque is getting applied around the fulcrum. Well, this leads us to, again, a scenario called static equilibrium for rotation. Just like we did static dynamics, where we just looked at objects at rest, or, the word static means it's not moving. We're looking at these situations where there is no net torque. The thing is, I'm not going to do a problem where you only have, you could technically say this is going to be true too, when you're at a constant rotation speed. Okay, obviously if there's no rotational acceleration, the object's not getting faster or slower, that means there must be no torque, but we'll bring that back up later. I am specifically looking at static equilibrium. Okay, objects not moving, but they would like to if they had the opportunity to get rid of something on the other side. Okay? So it's not rotating, but it has the possibility to do so. All right? In order to be in static equilibrium, the sum of all the clockwise torques has to equal the sum of all the counterclockwise torques. All right? Which makes sense. If something's trying to make it rotate one way, there has to be something that basically is trying to make it rotate the opposite. All right? And in other words here, if I don't have it written somewhere else, net torque equals 0 Newton meters. There is no net torque acting on this object. All right? And so this would be, an example would be if two people of equal mass get on either side of a seesaw and stay the exact same distance from the fulcrum, they should just stay perfectly balanced. They should stay kind of just sitting there in the air a little bit because both of them are countering each other's torque. All right? So if we start with an example here, two people are on a 10-meter long seesaw with the fulcrum in the middle. The seesaw has a mass of 150 kilograms. If one is 50 kilograms and sits at the end of one side of the seesaw, where must a person with a mass of 75 kilograms sit to make the seesaw not rotate? Okay. So this is a problem. These problems we always want to draw out. It's too much not to draw out something to kind of illustrate what's happening here. So I think I have step-by-steps trying to help you out with it. All right. So we have the length of the seesaw, 10 meters. We have the mass of the seesaw. Okay, we'll bring that in. The seesaw could try to rotate on its own depending on where the fulcrum is. The fulcrum, though, is in the middle. If one is 50 kilograms and the other one sits at the end of the seesaw, where must a person with a mass of 75 kilograms sit? So we can already think about this a little bit. Okay, if I do draw this out initially. Okay, we have a seesaw. The fulcrum's right in the middle. Okay, it's supposed to be right in the middle. Make this side a little bit longer. You have the 50-kilogram person all the way at the end, so a lighter person at the end. Where will the 75-kilogram person sit? Well, would they want to sit at the very end? No. They have a greater mass, which means they have a greater weight, a greater force. So where do they need to sit? They need to move in a little bit. We need to decrease that distance from the fulcrum. Okay, and we can have them balance out, which is what we're going to look at. All right. So how do we solve these problems? I do have basically a nice step-by-step way to look at this. All right. Always try to identify all the torques. Okay. As we just did, try to draw it out. And we're going to go through the whole thing. Draw. Okay. The 75-kilogram person will rotate that seesaw, and the 50-kilogram person will also rotate that seesaw. All right. So if I draw it out, I'll get this started, like I just did. Okay. I'm going to draw the people as boxes. You have one at the very end here. And you're going to have, I'm going to say, we already know he's going to be closer. They are applying a downward weight. This person over here at the end is applying a downward weight, which is perpendicular from the distance with the fulcrum. So this person is going to create a counterclockwise torque. What's the other person going to do? Well, they're applying a weight going straight down from a distance perpendicular. Okay. And therefore they would love to make the object rotate the opposite way. They'd like to make it rotate clockwise. Okay? The thing is, so that kind of answers my first bullet point right here. What about the seesaw itself? I already kind of mentioned that. Could the seesaw make it rotate on its own? What we have to do, this is a very, very, very important point, is for any problems, we will always look at all these extended objects, usually boards, bridges, beams, whatever you want to call them. All right? We will pretend that the object's weight is all hanging at the center of mass. All right? And that's technically because the particles on one side are trying to pull it down, the particles on the other side are trying to pull it down. So like if you look at it from almost down to an atomic perspective, each side is equally basically weighing it down. So why don't we just say, let's put all the weight right in the middle. That's where it's going to happen. Obviously, if there's more weight on the seesaw on one side than the other, then there's a shift in that center of mass, like we talked about a little bit with momentum. All right? Whichever side has more mass, that's what the center of mass is close to that side. If it's all a uniform object, the center of mass is in the middle, okay? Hanging at the object's center of mass. Well, in this case, it's going to be at the middle, okay? So this means that this force is being applied at the fulcrum. The weight of the seesaw is right at the fulcrum, which means how much distance is it from the fulcrum? 0. So even though there is a weight of the seesaw times the distance is going to be 0, so the torque by the seesaw is 0. In this problem, we're not going to see that in the very next one, but it's something we have to identify. If I say, why does the seesaw not make it rotate? It's because its weight is being applied at the center of mass, which is the center of this object, which is on the fulcrum. Distance is 0, 0 torque. Step 2, calculate your known torques. Okay? We would basically start calculating everything out. Okay? That's what we're looking at here. So again, let me go ahead and draw this out one more time. All right? The 50 kilogram weight over here, I'll write 50 kilograms, is applying a force. The whole thing is 10 meters long. It's a very large seesaw. Okay, 10 meters long. So that means that they are 5 meters from the fulcrum. So that means it would be 50 times 10, m times g. Okay, gotta find the weight. I'm doing force, not mass times distance. Force times gravity. Mass times gravity times the distance from the fulcrum. So you're going to get some large numbers here. So 50 times 10 is 50, or 500, wow, times 5 is 2,500 Newton meters. This torque would be counterclockwise. Is that positive or negative? Who knows? You get to pick that out in a moment. Okay? So the 50 kilogram person is trying to make it up, I guess the way I have it drawn is a different thing, clockwise. Okay, so basically this 50 kilogram person's on the other side. Okay, sorry. Stop it. The 50 kilogram person is on this side, based on my PowerPoint. Okay? So they are trying to apply this clockwise torque. Alright? Well, the thing is, what am I trying to solve for? I'm trying to solve for where is the 75 kilogram person going to go? Alright? This is the only torque I could solve for. It said solve for all known torques. We already said the torque of the seesaw, I'm just going to write SS, is 0. So all I'm missing is the torque of the 75 kilogram person. Well, the thing is, I know these two torques must be equal to each other because nothing is moving. So I can set them equal to each other. All right? The clockwise and counterclockwise torques equal each other. I know the clockwise torque is 2,500 Newton meters. That will equal force times distance. I know the force that this person is going to be applying is their weight, so that's 750. Divide that into 2,500. This person should sit at 3.3 meters from the fulcrum. From the fulcrum. Okay? Not from the end, from the fulcrum. So they would be only 1.7 meters from the end of the seesaw. All right? But we already knew that. We knew that they should be closer because they're heavier. So this gets us to our last problem. Come on, go away. What if the object doesn't have a clear fulcrum? Okay? Seesaws are easy because we know the fulcrum is usually in the center. Okay, almost always. And I mean, doors have a clear fulcrum. A lot of objects have a clear hinge, a clear point that the thing's going to rotate around. The thing is, we will get problems like bridges that have no clear fulcrum. All right, so this is a little bit more difficult. Actually, it's not. I mean, the surprising thing is it's not, but it surprises people. It confuses them. Okay. So again, this will usually work with objects on bridges. All right, I have seen some problems, some free responses where you have to figure out all this work and the person's walking across the bridge. Okay. So the thing is, the kind of it bothers people is if there's no clear fulcrum, you get to pick a spot to rotate around. Okay, just assume everything will rotate around that particular point. Now, the issue is, immediately when I say that, everybody goes, well, I want to choose the center, just like a seesaw problem, that was easy. That won't be that easy. Okay, that actually will make, it's going to be surprising where you might try to place the fulcrum. And actually, in many cases, we're going to want to place it at the end, you will see. Okay, all right, so that's pick an edge, and then all objects will have a clear distance from that point. Especially, again, they usually will give you the whole size of the bridge. If you pick the middle, there's going to be all these sizes you have to basically subtract out. If we pick a side that the quote-unquote fulcrum is located, everything can be measured from 0 up to wherever that object is from that point. Okay? So that is something I'm going to really encourage, and you'll see me do a problem with it too. So here we go. So we say Bob is standing on a bridge. He weighs, the bridge weighs 10,000 newtons. We feel bad if Bob weighed that much. So the bridge weighs that much. The span between pillars A and B is 80 meters, so that's the length of the bridge. Bob, whose mass is 100 kilograms, that's much more reasonable, stands 20 meters from the center of the bridge. So again, the wording can still be frustrating because they're going, wait, 20 meters from the center of the bridge toward pillar A. What? Is that 20 meters from pillar A? Don't overthink it. We'll figure that all out in a second. Okay? So, I mean, if we draw it out, if we still follow the exact same rules from the old problem, basically it's like this. We have these two pillars, B, A. The bridge itself is 80 meters long. Okay? The bridge is a uniform section, so the weight of the bridge will be right in the middle. This will be where the weight of the bridge is trying to make it rotate. Okay? It's a uniform bridge. Bob is 20 meters from the center, so Bob would be, actually, it turns out, yes, exactly 20 meters from the center, which means he's 20 meters from pillar A. It just happens that way. It happens that way. What if it was 100 meters long, I said 20 meters from the center? He'd be 30 meters from pillar A, but it happens that he's right in between pillar A and the center of the bridge. Okay? Moving on. Okay? The question is, find the force pillar A and pillar B exert to prevent the bridge from rotating. So, step 1, identify all sources of torque. But again, initially we go, oh no, there's no fulcrum. So my suggestion is don't pick the center. Don't pick the center. The center is going to be tough. Pick a side. Let's just say pillar A is where the fulcrum is. Okay? So everything's going to rotate around pillar A. The idea is this is the fulcrum. This would be our circular point. Everything's going to rotate either that would be counterclockwise or clockwise around this particular pillar A is what I'm referring to here. Okay? We draw everything out. Pillar B is 80 meters away, and pillar B is pushing upwards. There's a force from pillar B pushing upwards. A is pushing upwards as well, but it's pushing on the fulcrum, so is there any torque from A? No. The torque of A in my initial scenario here is 0 Newton meters because the fulcrum is at A. Okay? Bob is 20 meters from pillar A. He will provide a clockwise torque. The bridge is 40 meters from pillar A, the center of mass is, and will provide a clockwise torque. So let me go and draw that all out for you so you can see it. We got B and A. Okay? Technically, A applies an upward force. B applies an upward force. Again, this is our fulcrum. So B is going to try to push it up and back counterclockwise. All right, 80 meters away. The bridge is right at 40 meters and has a weight going down, so it's going to try to apply a torque clockwise. And then Bob is standing here nicely on the bridge, also going to try to apply a clockwise torque. So we have two clockwise torques countering a counterclockwise torque, and he is 20 meters away. Okay? So, to find all those torques. So I'm not going to go back to my picture. Pillar B, the torque of pillar B would be the force times 80. We don't know what that force is. That's what we're trying to solve for. What is the force that pillar B is using to basically push the bridge up? Bob's torque, we do know that he's 1,000 newtons. This is 100 times 10. He said it was 100 kilograms. Times 10 times 20 meters. He's producing a 20,000 newton meter clockwise torque. The bridge is applying 10,000 newtons of weight. He's a 1,000 kilogram bridge times 40 is providing 400,000 newton meters of clockwise torque. So I have a lot of clockwise torque and only one counterclockwise torque. But the thing is, what do I know about all these? They're going to be equal. The total clockwise will equal the total counterclockwise. That's step 3. Set them equal to each other. So torque of pillar B equals torque of Bob and torque of the bridge. Come on. Come on. So force times 80 equals 20,000 plus 400,000. Torque of Bob, torque of bridge. And basically, if we do all the math, the force that pillar B is providing is 5,250 newtons. Okay? Applying 5,250 newtons of force. Okay? And that's your answer. So that's pillar B. The thing is, the question is, what is the force that pillar A and pillar B are doing? What happens is people get very good at this rotational part, these setting the torques, and they forget basically Newton's, like essentially Newton's third law. There must be equal opposite forces if the object's not moving. Okay, if it's at rest. All right. So what we're looking at is that essentially, if I draw the bridge again, if I draw out the bridge, both pillars are pushing upwards, while Bob and the bridge are pushing downwards. The thing is the bridge moving up or down? Okay, not rotating anymore. We're not so much interested in rotating. We're just going, is the bridge moving up or down? The answer to that is no. So what can you tell me about the forces down in this system versus the forces upwards? They must be equal to each other. And that's what I'm getting at the end here. Since I now know that the total weight of the bridge and Bob is 11,000 newtons, that's how much is pushing down. The pillars must push back up with equal amount of force. Total sum of force equal. And so what I can do is I basically just set those two forces equal to each other. If pillar B holds up 5,250 newtons of this weight, how much will pillar A hold up? 5,750 newtons. The question there is, why does the pillar A hold up more weight? Why does it hold up more weight? And the answer is, why don't they hold up equal weight? They're both pillars at the end of the thing. Why don't they hold up equal weight? And it's all because of Bob. Where is Bob? Bob is closer to pillar A than B. And so pillar basically hit the center of mass of the Bob bridge system is slightly pushed over toward pillar A, which means pillar A is applying a greater force. Not torque, a greater force at this time. Now, if Bob walks across the bridge, where would Bob have to be in order for the for the two pillars to be exactly the same? That would be the center. What happens when Bob passes the center and goes towards B? B will increase, the force of B will increase while the force of A will decrease. So those are some of those other things that we will play around with as we continue doing problems with this. And that is it. Thank you.